Hello there, and welcome to the Sleepy Science Channel. Tonight, we're drifting into the mysterious world of atoms, the invisible and powerful realm that makes up everything you have ever perceived. They are the quiet architects of reality, patiently at work beneath every surface, every breath, and even everything you've ever thought. Atoms are everywhere, and yet scientists still don't fully understand them. They move in ways that challenge intuition, follow rules that seem almost dreamlike, and connect the smallest of objects to the grandest structures in the universe. From the air around you to the clothes on your body, atoms are always there, gently conforming to the laws of nature. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your shoulders loosen and allow your breathing to slow down. And let yourself unwind as we wander through the remarkable world of atoms. Let's begin. Atoms are mostly empty space, yet they somehow create everything solid around us. If you could enlarge a single atom until it filled a vast stadium, its nucleus would be smaller than a grain of sand. The rest of the atom would feel like open air, yet you cannot pass through a wall. This firmness comes from electric forces, not physical contact. The electrons surrounding atoms repel other electrons strongly when they come close. That invisible resistance is what your senses interpret as solidity. When you lean on a table, your body never truly touches it in a classical sense. Instead, layers of electric fields push back against each other. Even softness is just a gentler version of this resistance. The everyday world feels solid because atoms enforce boundaries with extraordinary consistency. Solidity is not fullness. It is agreement. It is empty space behaving with rules so reliable that your mind mistakes them for substance itself. Every atom in your body was forged inside ancient stars, long before Earth existed. In the early universe, only the lightest atoms existed, drifting through expanding space. Heavier atoms required furnaces far more extreme than planets could provide. Inside stars, intense heat and pressure forced smaller nuclei together, slowly creating new elements. Over long lifetimes, stars built the ingredients for complexity. When massive stars reached their final moments, they scattered those atoms outward in brilliant explosions. That material mixed into space and later gathered again into new stars and rocky worlds. Eventually, one such world formed oceans, chemistry, and life. The carbon in your cells, the iron in your blood, and the calcium in your bones all share this stellar origin. Your body is not merely on Earth. It is assembled from matter that once shone. You are a quiet continuation of ancient cosmic fire. An atom's nucleus is unimaginably small, yet it contains nearly all of its mass. Nearly all the weight of an atom is concentrated into its nucleus, a region astonishingly compact. Protons and neutrons cluster there, bound by a force strong enough to overcome electrical repulsion. Electrons define the atom's size and behavior, yet they contribute almost nothing to its mass. This creates a strange imbalance between scale and substance. Most of what makes an atom heavy is hidden deep inside. The forces at work within the nucleus are among the strongest in nature. When that balance changes, tremendous energy can be released. This is why nuclear processes differ so dramatically from chemical ones. The nucleus reveals that power does not require size. It only requires intensity. Within something nearly invisible lies a concentration of matter capable of shaping stars, planets, and the long history of the universe itself. The same atoms form your breath, the oceans, distant planets, and glowing stars. The oxygen you breathe is not unique to Earth. It is found in rocks, water, and distant cosmic clouds. Hydrogen, the simplest atom, dominates the universe and fuels the steady burning of stars. Carbon appears in meteorites and interstellar molecules, showing that complex chemistry begins far from planets. Nitrogen helps stabilize Earth's atmosphere, yet it also drifts between stars in cold darkness. Silicon and oxygen pair to build rocky worlds across the cosmos. What changes from place to place is not the cast of atoms, but the arrangement. Familiar ingredients assemble into unfamiliar forms. Your breath shares its atomic makeup with oceans and suns alike. The universe is not built from endless novelty. It is built from reuse, rearrangement, and patience, working on unimaginable scales of time and space. Atoms bond together to form molecules, then rearrange into entirely new substances. Atoms rarely exist alone. They connect, separate, and reconnect in patterns that create new materials. When bonds form, energy is shared and shapes emerge. Rearranging those bonds can turn the same atoms into substances with entirely different properties. Carbon atoms can become transparent crystal or soft black powder, depending on structure. In living cells, atoms constantly shift partners to build sugars, fats, and proteins. In fire, atoms rearrange rapidly, releasing heat and light. Even rust is a slow transformation, where iron adopts new companions from the air. The atoms remain, but their relationships change. Chemistry is not destruction or creation. It is storytelling through connection. By rearranging bonds, matter learns new behaviors, new roles, and new possibilities, all while using the same underlying pieces again and again. Quantum rules allow a single atom to exist as possibility until it is observed. At very small scales, atoms do not behave like tiny objects following clear paths. Instead, they are described by probabilities. An atom can exist as a range of possible positions or states at once. Experiments show that single atoms can interfere with themselves, as though exploring multiple options simultaneously. Only when a measurement is made does a specific outcome appear. This is not confusion or randomness in the everyday sense. It is a fundamental feature of nature. Observation itself plays a role in shaping results. The atomic world does not always settle on an answer until asked a question. This challenges intuition shaped by larger objects. Atoms remind us that certainty is not guaranteed. Reality, at its smallest scale, allows room for possibility before committing to a single experience. Removing or adding one electron can completely change how an atom behaves. An atom with a balanced number of electrons is electrically neutral. Change that balance by one, and everything shifts. The atom becomes charged, gaining new tendencies and interactions. These charged atoms, called ions, are everywhere. In your body, they help transmit nerve signals and regulate muscle movement. In oceans, they influence chemistry and conductivity. In batteries, they store and release energy in controlled ways. In the air, ions form around energetic events like lightning. What makes this remarkable is how small the change can be. One electron is tiny beyond imagination, yet its presence or absence can decide whether an atom clings tightly to others or repels them. A single missing or extra electron can determine stability, reactivity, and function. Great consequences often begin with the smallest adjustments. Some atoms remain stable for eternity, while others transform in moments. Not all atomic nuclei are equally comfortable with their internal balance. Some persist unchanged for spans longer than the age of the universe. Others carry tension that eventually releases through transformation. When this happens, the atom becomes a different element altogether. This process occurs spontaneously and follows predictable averages, yet individual events remain uncertain. In nature, these transformations quietly warm Earth's interior and shape geological history. In medicine, carefully chosen unstable atoms help doctors observe hidden processes inside the body. What makes this phenomenon so striking is its mixture of patience and suddenness. A nucleus may wait millions of years, then change in an instant. Atomic time does not always match human expectations. Stability and change coexist, written deep into matter itself. The periodic table is a roadmap showing how different atoms prefer to interact. The periodic table organizes atoms by repeating patterns rather than simple order. Move across a row, and atoms gradually change how strongly they attract electrons. Move down a column, and atoms grow larger, altering how easily they form bonds. This structure explains why certain elements behave like close relatives. They react in similar ways, form similar compounds, and appear together in nature. The table also highlights extremes, such as atoms that react eagerly and atoms that resist reaction almost entirely. It allows scientists to predict behavior before experiments begin. The table is not just a list. It is a guide to tendencies, preferences, and possibilities. By reading it carefully, we gain insight into how matter is likely to behave long before atoms ever meet. Your body is a living pattern made from countless atoms in constant motion. Even when you are resting, the atoms that compose you are busy. Air flows in and out, bringing atoms that briefly become part of you. Water circulates, carrying dissolved minerals through tissues. Cells build, repair, and replace structures continuously. Some parts of your body renew quickly, while others persist longer. What remains consistent is the pattern, not the individual atoms. Over time, many of the atoms that once formed you move on, replaced by others. Your identity is maintained through organization rather than permanence. You are less like a statue and more like a river. Familiar because the shape endures, even as the contents change. Life is an ongoing arrangement, sustained moment by motion, exchange, and balance. The word atom originally meant indivisible, yet atoms themselves contained smaller parts. For a long time, atom was a promise that matter had a final, unbreakable unit. Then curiosity kept peeling the idea open. What once seemed like a tiny, hard bead turned out to have a crowded interior, with lightweight electrons surrounding a dense nucleus of protons and neutrons. And even those pieces have deeper structure, revealed through high-energy experiments that treat nature like a detective story. Each discovery did not ruin the concept of atoms, it made it richer. It showed that the universe is built in layers, like nested worlds. When you hold a coin or sip water, you are holding a system with inner architecture, not a featureless speck. The word stayed the same, but the meaning grew into something far more surprising. Ancient philosophers imagined atoms using thought alone, centuries before experiments. In a world without telescopes, particle detectors, or chemistry sets, some minds still asked a daring question. What if everything is made from tiny pieces too small to see? Think of the leap that requires to trust logic over the evidence of the senses. The idea competed with other views, like matter being continuous, endlessly divisible, and smooth. There was no quick way to settle it, so it lived as philosophy rather than measurement. Yet the core intuition was powerful. It suggested that changing the arrangement of unseen parts could change the nature of a material. Long before laboratories, this was a way of explaining why wood and stone behave differently and why substances can transform. It is a reminder that human curiosity often reaches the right direction first and only later builds the tools to follow. Modern atomic theory emerged from careful measurements rather than direct observation. Atoms did not become real to science because someone finally saw them with their eyes. They became real because numbers began to behave as if atoms had to exist. When chemicals reacted, they combined in consistent ratios, over and over, even when experiments were repeated by different people in different places. Matter seemed to arrive in neat packages, not in arbitrary amounts. That steady arithmetic suggested hidden units behind the scenes, quietly enforcing order. It was like hearing footsteps in the next room and realizing someone must be there, even if the door stays closed. This approach turned atoms into something testable. It replaced speculation with prediction. You could weigh ingredients, watch reactions, and infer what must be happening at a scale too small to see. The atomic world became trustworthy because it left reliable fingerprints in everyday measurements. Dmitri Mendeleev predicted unknown elements before they were ever discovered. Imagine building a chart of the known elements and noticing a rhythm, like a melody that keeps repeating. Mendeleev saw patterns in properties and reactions that suggested the list was incomplete. Instead of forcing the data to fit what was already known, he trusted the pattern and left gaps. Those gaps were not mistakes. They were invitations. He described what the missing elements should be like, based on the neighbors around them. Later, new elements were found that matched those expectations with striking accuracy. This was not luck. It was a sign that atoms follow deep rules, and that those rules can be read like a map. The periodic table became more than a catalogue. It became a predictive tool, a way of pointing to things that exist even before human beings have named them. The discovery of the electron revealed that atoms were not solid after all. For a while, atoms were imagined as the smallest solid bits of matter, like microscopic grains. Then experiments with electricity changed the story. Streams of charged particles could be pulled from within matter itself, showing that something smaller was hiding inside atoms. Those particles behaved the same no matter what material produced them, which hinted at a universal ingredient. That was the electron, a tiny carrier of negative charge that helped explain sparks, currents, and the strange behavior of gases under voltage. Once the electron was known, the atom could no longer be pictured as a simple lump. It had parts, structure, and internal motion. It also suggested that electricity was not a mysterious fluid, but a behavior of matter at a very small scale. The discovery opened a door, and behind it was a much more intricate universe than anyone had expected. A thin sheet of gold helped uncover the dense atomic nucleus. In one famous experiment, scientists aimed a beam of tiny charged projectiles at an ultra-thin foil of gold. If atoms were soft and spread out, the beam should have passed through with only mild deflection. Most of it did. But a few particles bounced back at sharp angles, as if they had struck something hard and concentrated. That rare recoil was the shock. It meant the atom's positive charge, and almost all its mass, were not smeared throughout the whole atom. They were packed into a compact center. The atom was revealed as mostly open space with a dense core, like a cathedral with a heavy stone altar at its heart. This result changed the whole blueprint of matter. It also showed how science often advances, not by what usually happens, but by paying close attention to the surprising few events that refuse to fit the expected story. Early atomic models evolved as scientists followed evidence rather than intuition. The history of atoms is a lesson in humility. Each generation built a model that seemed sensible, Then nature quietly proved it incomplete. The earliest pictures were simple because the evidence was simple. As new experiments arrived, the models had to change, even when the changes felt strange. Atoms went from solid spheres to structures with embedded charge, to a nuclear center with surrounding electrons, and onward into more abstract descriptions. What is beautiful is not that scientists got it wrong at first, but that they let the universe correct them. They treated models as tools, not as beliefs. When a model stopped matching results, it was revised or abandoned. That is how knowledge grows sturdy. The atom became clearer not through stubbornness, but through flexibility. The story reminds us that understanding deepens when we stay willing to update our mental picture as new clues appear. Quantum mechanics replaced tidy atomic orbits with clouds of probability. It is tempting to picture electrons circling a nucleus like tiny planets around a sun. That image feels calm and familiar. But the atomic world refused to stay that neat. Experiments showed that electrons act in ways that cannot be captured by a single definite path. Instead, their behavior is described by probabilities, as if nature provides a range of likely locations rather than a precise track. This is where the idea of an electron cloud comes from. It is not a fuzzy blob of matter, but a map of where an electron is more or less likely to be found. That shift changes how we imagine atoms. They become less like miniature machines and more like patterns of potential. The rules are still precise, but the picture is different from everyday experience. Quantum mechanics did not make atoms vague. It made them deeper and far more surprising. Atoms were first imaged indirectly through their effects, not traditional photography. For most of history, atoms were known by what they did, not by what they looked like. They explained chemical ratios, electrical behavior, and the colors of light, long before anyone could claim an image. When instruments finally approached atomic scales, they did it in an unexpected way. Instead of taking a picture with light, they traced surfaces by measuring tiny forces or currents, point by point, as a probe moved across. From those measurements, an image could be built, like a landscape made from touch rather than sight. It is a clever workaround, because visible light is too coarse to resolve individual atoms directly. The first atomic pictures were therefore translations, turning invisible interactions into visible shapes. That achievement is part science, part artistry. It let humanity do something once thought impossible, not by seeing smaller, but by measuring smarter. Isotopes are atoms of the same element that quietly differ in weight. Two atoms can behave almost like twins in chemistry, yet still carry a subtle difference in their nuclei. If they have the same number of protons, they belong to the same element and share a chemical identity. But if they carry different numbers of neutrons, their mass changes, and that can matter in surprising ways. Some isotopes are slightly heavier and move differently through physical processes, like evaporation or diffusion. That makes them useful as tracers, because their signatures can be detected without changing the basic chemistry of what they are mixed into. You can follow where water has traveled or how a substance moves through a system simply by tracking the isotope pattern. Isotopes also explain why atomic weights are not always neat whole numbers on the periodic table. Nature mixes versions, and the average becomes the number we write down. The number of protons defines an element's identity without exception. If you want the universe's simplest naming rule, it is this one. Count the protons in the nucleus, and you have the element. 1 proton is hydrogen, 2 is helium, 6 is carbon, and that count never changes unless the nucleus itself changes. You can add neutrons and make heavier versions, and you can add or remove electrons and change the charge, but the element name stays anchored to its proton number. That is why the periodic table is really a proton table in disguise. It is also why nuclear reactions feel so dramatic. They are not just shuffling bonds. They are rewriting identity. In laboratories and stars, when a nucleus gains or loses protons, matter crosses a boundary into a new element, with new chemistry and a new role in the world. Changing the neutron count creates isotopes with different physical behaviors. Neutrons are quiet passengers in the nucleus. They do not change an element's name, but they do change its mass, and mass can subtly steer how atoms move. A heavier isotope of an element tends to respond a little differently in processes like evaporation, freezing, and diffusion. Over long times, those tiny differences can leave detectable patterns in ice, ocean water, and minerals, like a gentle signature written into the material itself. Scientists use these patterns to trace pathways, compare conditions, and reconstruct histories, often without altering the chemistry that made the substance useful in the first place. It is a beautifully delicate idea. Two atoms can behave almost identically in reactions, yet still travel and sort themselves differently because one nucleus carries a few extra neutrons. Nature notices weight, even when chemistry barely does. Certain isotopes act as natural clocks for dating ancient materials. Some atoms carry a built-in timer, not because they tick like gears, but because they change in a steady statistical way. An unstable nucleus gradually transforms into a different one, and the pace of that transformation can be remarkably reliable. If you know how quickly a parent isotope turns into its daughter, then measuring their ratio becomes a way of estimating elapsed time. What makes this feel almost magical is that the clock is inside the matter itself. A crystal can form, lock certain atoms in place, and quietly keep time while continents shift above it. Different isotope clocks cover different spans, from relatively recent history to the deep ages of planets. The trick is choosing the right clock for the question and reading it carefully, like a watch that only speaks in ratios. Carbon-14 allows scientists to date once-living objects from the recent past. While an organism is alive, it continually exchanges carbon with its environment. That keeps a predictable mix of carbon types in its tissues. Once it dies, that exchange stops, and one particular carbon isotope begins to dwindle as it transforms over time. By measuring how much remains, scientists can estimate how long it has been since the organism stopped taking in new carbon. This technique works on things that were once part of a living system, like wood, cloth, bone, and seeds. It does not date the age of a rock that was never alive, and it is most useful within a limited window of time where enough signal remains to measure. When it does work, it can place a human artifact or an ancient campfire into a clearer timeline, turning mystery into history. Radioactive atoms reveal Earth's age through slow and predictable decay. Earth is far older than any written record, and even older than the oldest fossils. To reach those timescales, scientists rely on isotope systems that change very slowly, like hourglasses designed for planets. In certain minerals, parent isotopes become daughter isotopes at a measured pace, and those minerals can protect the evidence like a vault. Zircon crystals are especially famous because they can preserve their internal chemistry through intense heat and pressure, surviving long geological journeys. By comparing parent and daughter amounts inside such crystals, researchers can estimate when the crystal formed, and therefore place a minimum age on parts of Earth's crust. Using multiple methods across many samples, a coherent picture emerges of a planet that has been evolving for billions of years. The atoms do not guess. They record, patiently, in ratios. Atoms become ions when electrons are lost or gained. Electrons are the negotiators of chemistry, and when an atom loses one, it becomes positively charged. When it gains one, it becomes negatively charged. This shift can completely change how it behaves around other atoms, because charge creates strong attraction and repulsion. In everyday life, ions are responsible for many of the things we experience as function. They help solutions conduct electricity, they influence how minerals dissolve, and they play central roles in biological systems that depend on tiny electrical gradients. Even the word ion carries a sense of motion, because charged particles respond to electric fields and drift through liquids and tissues. Ions can be gentle, like the ones that maintain balance in your body, or dramatic, like the ones involved in sparks and lightning. Either way, the transformation begins with a simple event, an electron leaving or arriving. Table salt forms when sodium and chlorine exchange electrons completely. Sodium is eager to let go of one electron, and chlorine is eager to accept one. When that exchange happens, each becomes an ion, one positive and one negative, and their attraction is immediate. But table salt is not built from pairs alone. Those ions arrange themselves into a repeating lattice, a three-dimensional pattern that extends outward in all directions. That structure explains familiar salt behaviors. It forms crystals with flat faces because the internal order is so regular. It dissolves in water because water molecules can surround and separate the ions. It conducts electricity when dissolved because the ions can move freely in solution. The most striking part is that metallic sodium is soft and reactive, and chlorine gas is hazardous, yet together they produce a stable, edible mineral. A simple electron trade can turn danger into dinner. Metals conduct electricity because some electrons move freely between atoms. In many materials, electrons are tied tightly to specific atoms, which makes electric current difficult. Metals are different because some of their electrons are shared across many atoms at once. You can imagine them as a mobile crowd rather than individuals confined to one address. When you apply an electric field, that crowd shifts and the motion becomes current. This freedom also helps explain why metals tend to be shiny. Their roaming electrons interact strongly with light and reflect many wavelengths back to your eyes. It also helps explain why metals can be shaped. If atomic bonds are not too directional, layers can slide while the shared electron network still holds everything together. Copper wiring, aluminum foil, and gold leaf all depend on this same basic behavior. Metals are not just solid matter. They are solid matter with a built-in highway for electrons. Diamonds form when carbon atoms lock into an exceptionally rigid structure. Carbon is a master of arrangement, and diamond is one of its most disciplined forms. Each carbon atom bonds to four others in a repeating pattern that spreads strength evenly through the entire crystal. That geometry makes diamond extremely hard because there are no easy planes for the structure to slip along. It is also why diamonds can conduct heat so well, even though they do not conduct electricity in the way metals do. Many diamonds form deep within Earth under intense pressure, then travel upward through volcanic processes that deliver them closer to the surface. Their beauty is not only their sparkle. It is the story of atoms choosing a shape that is both simple and unbelievably strong. The same element can be soot in a chimney or a gemstone in a ring, and the difference is nothing but atomic architecture. Graphite forms when carbon atoms arrange into slippery layered sheets. Graphite is carbon taking a completely different approach. Instead of bonding in all directions, carbon atoms form broad flat sheets with strong bonds within each sheet. Between sheets, the attraction is much weaker, so the layers can slide over one another easily. That is why graphite feels slippery and why it works as a lubricant in certain conditions. It is also why a pencil leaves a mark. Tiny flakes shear off and cling to paper fibers, creating a visible trail. Graphite has another surprising talent. It can conduct electricity because electrons can move across those carbon sheets more freely. This combination of softness and conductivity makes graphite useful in everything from writing to industry. And it has become even more fascinating in modern science because a single isolated layer behaves in extraordinary ways. Once again, carbon shows its gift. Same element, new structure, new world. Water's unusual properties come from the specific arrangement of its atoms. Water looks simple, but its shape is quietly powerful. The oxygen atom sits at the center, with two hydrogen atoms attached at an angle, not in a straight line. That bend creates an uneven pull on electrons, giving the molecule a positive side and a negative side. Because of that, water is naturally attracted to charged and polar substances, which is why it is such an effective solvent. It can surround particles, separate them, and carry them through living cells, rivers, and pipes. This same geometry helps explain why water has a surprisingly high heat capacity, meaning it can absorb a lot of warmth before it feels hot. It buffers climates, steadies body temperature, and softens the sharp edges of seasonal change. A small bend in a tiny molecule ends up shaping the entire planet's habitability. Hydrogen bonding gives water its remarkable ability to support life. Water molecules do not simply drift past one another. Their slight charges make them link up through hydrogen bonds, forming a shifting network that is strong enough to matter, yet flexible enough to renew instantly. This network gives water its cohesion, the way droplets hold together, and its surface tension, the way a pond can behave like it has a delicate skin. It also allows water to cling to other surfaces, helping it climb narrow spaces in soils and in the tiny channels of plants. Hydrogen bonding raises water's boiling point far above what you might expect for such a small molecule, keeping oceans liquid across a wide range of temperatures. Inside living cells, this bonding helps stabilize the shapes of biological molecules and creates the watery environment where chemistry can proceed gently and reliably. Life is not just in water. Life is possible because water bonds. Ice floats because frozen water expands at the atomic level. Most substances become denser when they freeze, but water is famously rebellious. As liquid water cools, its molecules slow down and begin to settle into a more ordered arrangement. When it freezes, hydrogen bonds guide the molecules into a crystalline structure that holds them slightly farther apart than they were in the liquid. That extra spacing means the same mass now occupies more volume, so the solid becomes less dense and floats. This one quirk changes the destiny of lakes and oceans. Ice forms on the surface first, creating an insulating layer that slows further freezing. Beneath that lid, liquid water can remain, protecting fish, plants, and microscopic life through winter. Floating ice also reflects sunlight, influencing climate and the balance of heat on Earth. A subtle expansion becomes a planetary safeguard. Glass behaves like a frozen liquid with atoms locked out of order. Glass looks like a solid, feels like a solid, and shatters like a solid, yet its internal structure tells a different story. In many solids, atoms settle into tidy, repeating crystals. In glass, the atoms cool too quickly to line up that way. They become trapped in a disordered arrangement that resembles a liquid paused mid-motion. This is why glass is called an amorphous solid. Its atoms are not randomly scattered, but they lack the long-range repeating pattern of a crystal. That unusual structure gives glass its transparency, because light can pass through without being scattered by a grainy crystal texture. It also gives glass its brittleness, because stress does not have predictable slip planes to relieve it. Every window is a snapshot of atoms caught between states, holding a memory of flow. Bone strength comes from mineral crystals built from organized atoms. Bone is not a lifeless scaffold. It is a living composite material, engineered by biology with atomic precision. Its strength comes from tiny crystals of a mineral called hydroxyapatite, made largely from calcium and phosphate. These crystals are embedded within a flexible framework of collagen, a protein that behaves like tough woven rope. The mineral provides hardness and resistance to compression, while collagen provides resilience and resistance to cracking. Together, they create a structure that is lightweight, strong, and capable of repair. At the microscopic level, bone is layered and patterned, with mineralized fibers arranged to handle forces from many directions. Even the hollow spaces are part of the design, reducing weight while preserving strength. When you walk, jump, or stretch, you are trusting an atomic architecture built to balance stiffness and flexibility, and to renew itself as life demands. DNA stores biological instructions using atoms arranged into repeating patterns. DNA is a long molecule that works like a physical library, written in chemistry rather than ink. Its backbone is a repeating chain of sugars and phosphates, forming two strands that run side by side. Along those strands, 4 types of bases act like letters, pairing in specific ways so the two strands fit together neatly. The sequence of those bases carries instructions for building proteins, timing development, and guiding the everyday work of cells. What makes this extraordinary is that information is stored as an arrangement of atoms, a pattern that can be copied with high accuracy. When a cell divides, the strands separate, and each guides the construction of a partner strand. That simple pairing rule allows life to persist, adapt, and evolve over generations. In every cell, atoms become memory, and chemistry becomes inheritance. Proteins fold into precise shapes because atoms seek energetic balance. A protein begins as a simple chain of amino acids, like beads on a string. But it cannot do much until it folds into a specific 3-dimensional shape. That folding happens because different parts of the chain attract, repel, and negotiate for the most stable arrangement. Some regions avoid water and tuck inward, while others prefer to face outward. Weak interactions, like subtle attractions between atoms, add up into a strong overall preference for one shape over many alternatives. When folding succeeds, the protein becomes a tool, able to carry oxygen, cut molecules, signal messages, or build structures. When folding fails, the consequences can be serious because shape is function in the molecular world. What is beautiful is the economy of it. The chain does not need a conscious designer. Atomic forces guide it toward balance, and life builds complexity from that quiet tendency. Smell begins when airborne molecules interact with atomic receptors in your nose. Every scent is a physical encounter. Tiny molecules drift into your nose and dissolve into a thin layer of mucus where they can meet receptors on nerve cells. Each receptor is a protein with a shape and an electrical landscape that make it sensitive to certain molecules more than others. When a molecule fits well enough, it triggers a change in the receptor that starts an electrical signal. Your brain then interprets combinations of signals as particular smells, like smoke, citrus, rain, or coffee. This is why scent can feel so vivid and emotional. It is not just a label, it is a pattern of molecular events turned into experience. A single odor often contains dozens of different molecules, each adding a note. Smell is chemistry translated into memory, and it begins with atoms finding their places in a receptor's subtle contours. Taste arises when atoms trigger tiny electrical signals on the tongue. Taste is not a single sense, but several pathways working together. For salty and sour, ions directly influence channels in taste cells, changing electrical balance and triggering signals. For sweet, bitter, and savory, larger molecules activate receptors that set off internal cascades, like a tiny chain reaction inside the cell. These pathways send messages through nerves to the brain, where they become flavor, especially when combined with smell and texture. Taste is also a guardian. Bitterness often signals potential toxins, while sweetness hints at energy-rich foods. Saltiness helps track essential minerals, and sourness can warn of spoilage. Yet taste is not just survival. It is pleasure, culture, and memory, all built on atomic interactions at the surface of the tongue. A meal becomes an experience because atoms, ions, and molecules can speak to nerves in a language your brain understands. Color exists because atoms absorb certain wavelengths of light. Light carries energy, and atoms have specific energy gaps that electrons can move across. When light strikes a material, certain wavelengths are absorbed because they match those gaps, while other wavelengths are reflected or transmitted. What you see as color is the portion that remains. In pigments and dyes, special molecular structures are tuned to absorb particular parts of the spectrum, producing vivid reds, blues, and yellows. In metals, shifting electrons can reflect light in distinctive ways, giving gold its warm tone and copper its reddish glow. In nature, chlorophyll absorbs red and blue light efficiently, leaving green to reach your eyes, which is why plants look the way they do. Color is not painted onto the world. It is a conversation between light and atoms, translated by your nervous system into a feeling of brightness and hue. Excited atoms release light at specific colors unique to each element. When an atom absorbs energy, its electrons can jump to higher energy states, like stepping onto higher rungs of a ladder. Those rungs are not continuous. They come in specific allowed levels, different for each element. When the electron falls back down, it releases the extra energy as light. The color of that light depends on the size of the energy step, and that makes it a signature. Neon produces its famous reddish glow, while copper can give green and blue hues, and sodium often shines yellow. These are not artistic choices. They are atomic rules, spoken in photons. In a lab, a hot gas can be made to glow, and the emitted colors can be split into sharp lines, like a barcode. Each element has its own pattern, which means atoms can be identified by their light alone. Astronomers identify distant elements by reading atomic light signatures. Stars are too far away to sample directly, yet they constantly send information. Their light carries thin, dark, or bright lines that appear when atoms absorb or emit specific wavelengths. When astronomers spread starlight into a spectrum, those lines become a readable code. Each element stamps the light with its own pattern, allowing scientists to tell what a star is made of, even across immense distances. This is how we learn about the chemistry of galaxies, the makeup of nebulae, and the composition of planets passing in front of their suns. It is a kind of remote sensing that feels almost like magic, but it is simply atoms being consistent. A calcium atom in a star behaves like a calcium atom in a laboratory on Earth. The universe speaks one language, and spectroscopy is how we listen. By reading light carefully, we find the elements in places we will never touch. Helium was discovered in sunlight before it was found on Earth. Helium has one of the most poetic discovery stories in science. During the study of a solar eclipse, astronomers examined sunlight and noticed a spectral line that did not match any known element. The line was real and repeatable, which meant something in the sun was absorbing or emitting a unique wavelength. Scientists proposed a new element and named it after the sun, using the Greek word for it. Only later was helium found on Earth, hidden in minerals and released from underground sources. This reminds us that the sky can be a laboratory. The sun revealed a substance that our planet kept mostly concealed. It also shows the power of atomic signatures. A single, unexpected line in light was enough to announce that a new kind of atom existed. The discovery arrived not by digging downward, but by looking up. Flame colors reveal which atoms are being energized by heat. Heat can be a storyteller. When you place certain substances into a flame, the temperature energizes their atoms and ions, allowing electrons to jump and fall, releasing light as they return. That light can tint the flame with distinct colors. Sodium often turns a flame bright yellow. Potassium can lean toward a pale violet. Copper can produce green or blue. Fireworks rely on the same principle, but a flame test makes it intimate, like watching atoms whisper their identity. This is not about the flame itself. It is about the energized particles within it. The color can reveal trace contaminants too, because even small amounts of a substance can shine strongly. In chemistry education, it becomes a vivid moment where invisible structure becomes visible. A flame can become a quick, dramatic window into atomic behavior, turning heat into color-coded evidence. Lasers work by forcing atoms to emit light in perfect unison. Ordinary light is a busy crowd. Photons are emitted at random times and in random directions, so the wave pattern is messy. A laser is different because it is organized. Inside a laser medium, atoms are pumped with energy. So many are waiting in an excited state. When one atom emits a photon, that photon can stimulate another excited atom to emit an identical photon, matching direction, phase, and wavelength. This chain reaction creates a beam that is unusually pure and focused. Because the light is so coordinated, lasers can travel far without spreading much, and they can be aimed with precision. That is why they are used in eye surgery, barcode scanners, fiber optics, and delicate measurements. The strange part is how cooperative the atoms become under the right conditions. Lasers are not just bright. They are disciplined. They are atoms persuaded to sing the same note together at the same time. Fluorescent materials glow when atoms quickly re-release absorbed energy. Fluorescence begins when a material absorbs high-energy light, often invisible ultraviolet. That energy excites electrons into higher states. Then, almost immediately, the electrons drop back down, releasing part of the energy as visible light. The glow appears quickly and fades quickly, stopping almost as soon as the excitation stops. This is why fluorescent posters look electric under blacklight, and why some minerals seem to awaken in a darkened room. The color depends on the internal structure of the material, which shapes the energy steps available. Fluorescence is used in science and medicine too, because glowing tags can be attached to molecules and tracked, revealing hidden patterns. It is like giving the microscopic world a lantern. What makes it so satisfying is the speed. Light goes in, and a different light comes back out, transformed by atomic rules into a visible signal. Phosphorescent materials glow longer because atoms release energy slowly. Phosphorescence looks like magic because it lingers. A material absorbs energy, often from light, and then continues to glow after the lights go out. The secret is that some excited electrons get trapped in states that are not eager to release their energy. They sit there, holding it, until thermal motion or chance allows them to return to lower states. When they finally do, the stored energy is released as visible light. That slow escape is why glow-in-the-dark objects fade gradually rather than instantly. Different materials have different trap depths, which changes how bright the glow is and how long it lasts. The effect can last minutes or hours, depending on the chemistry. Phosphorescence is a reminder that the atomic world has timing as well as color. Light can be captured, held, and released gently, like a slow exhale. It turns illumination into a delayed echo. Fireworks shine brightly because metal atoms emit vivid colors. A firework is a controlled burst of chemistry designed to heat atoms intensely. Inside the shell are compounds that burn rapidly, producing heat, gas, and bright light. Metal salts are included because their atoms emit specific colors when energized. Strontium can create rich reds. Barium can produce greens. Copper often gives blue tones, though it is tricky to keep stable at high temperatures. The shape of the burst is guided by how the shell is packed, while the color is guided by which atoms are present. Timing compounds control when different sections ignite, so one explosion can unfold in stages. What you see as a single dazzling flower in the sky is really a carefully arranged sequence of atomic events. Each glowing point is a miniature laboratory where excited atoms drop back down and release photons. Fireworks are chemistry made public. They are atoms performing their signatures at full volume. Sodium atoms give streetlights their familiar warm yellow glow. Some streetlights have a distinctive golden yellow color that feels almost nostalgic. That hue comes from sodium, whose electrons have energy steps that strongly favor emission in the yellow region. In a sodium lamp, an electric current excites sodium atoms in a gas. As electrons return to lower states, they emit light in very specific wavelengths, producing a concentrated yellow glow rather than a broad rainbow. This makes sodium lighting efficient for illumination, but less ideal for showing true colors, since the light is not balanced across the spectrum. Under it, red and blue objects can look strangely similar. Yet there is a beauty to its simplicity. The lamp is not painting the street yellow. The atoms are releasing their preferred photons. It is a reminder that lighting is not just brightness. It is chemistry. Even the mood of a nighttime city can be shaped by which atoms are chosen to glow above the pavement. Auroras appear when atmospheric atoms collide with solar particles. High above Earth, the atmosphere becomes thin, and space begins to feel close. Streams of charged particles from the Sun arrive and are guided by Earth's magnetic field toward polar regions. There, they collide with atoms and molecules in the upper air, transferring energy. Those atmospheric particles become excited, and as they relax, they emit light. Oxygen can produce green and sometimes red glows at different altitudes. Nitrogen can contribute blues and purples. The shifting curtains and ripples come from changes in particle P-K and magnetic conditions, shaping where the collisions happen moment to moment. An aurora is not sunlight reflected. It is Earth's atmosphere being energized from within, like a living canvas. It connects our planet to the Sun through atomic interactions that happen silently in the dark. The sky becomes a place where invisible space weather turns into visible color, and atoms turn impact into beauty. Atoms rarely touch, yet electromagnetic forces create the feeling of solidity. When you press your palm to a tabletop, it feels like contact, but it is really a standoff. The outer electrons in your skin and the outer electrons in the table push back through electric repulsion. On top of that, quantum rules discourage identical electrons from sharing the same state, which adds an extra layer of resistance. Together, those effects create the firm boundary your nerves interpret as touch. That is why pressing harder does not bring you closer to the atoms inside the table in any simple way. You are increasing the force in the electromagnetic tug-of-war, not closing a literal gap until things merge. Even a soft pillar relies on the same fundamental pushback. The difference is how the atoms are arranged and how easily the material can deform. Solidity is a sensation built from forces that never need actual contact to feel real. The emptiness inside atoms explains why compression has limits. Because atoms are mostly space, you might imagine matter could be squeezed almost endlessly. In practice, it resists strongly once you try to force electrons into tighter quarters. As you compress a material, electron clouds begin to overlap, and the energy cost rises steeply. It becomes harder and harder to push matter into a smaller volume, not because you run out of room, but because the rules of electrons push back. This is why materials have immeasurable stiffness, and why even the strongest presses meet a wall of resistance. In extreme laboratories, scientists use diamond anvil cells to mimic the crushing pressures found deep inside planets. Under those conditions, atoms rearrange into denser structures, sometimes forming unexpected phases of matter. Yet even then, nature does not let you compress without paying. The seeming emptiness is not free space. It is a structured domain, guarded by electric forces and quantum constraints. Atomic vibrations increase as temperature rises. In a solid, atoms are not frozen in place like decorations on a shelf. They vibrate around their positions, constantly jiggling in tiny rhythms. As temperature rises, those vibrations grow stronger and more energetic. This extra motion helps explain why most materials expand when heated, because the average spacing between atoms increases slightly as they wobble. It also explains why heat can soften solids. With more vibration, atomic bonds are more easily distorted, and materials can become less rigid. On the microscopic level, these vibrations travel as collective waves through the lattice, carrying energy from one region to another. That is one reason a metal spoon left in hot tea warms along its length. Temperature, in this sense, is not an abstract number. It is a measure of how intensely atoms are shaking and how much energy they are sharing through that motion. Absolute zero represents the lowest possible atomic motion. Absolute zero is the point where a substance has as little thermal energy as nature allows. It is not simply very cold. It is a fundamental limit tied to the way energy comes in quantized steps. In practice, it cannot be reached perfectly, only approached more and more closely. Even near that limit, atoms and particles do not become perfectly still. Quantum mechanics allows a residual restlessness called zero-point motion, a kind of built-in jitter that cannot be removed. When scientists cool certain gases to extremely low temperatures, they can enter unusual states where many particles behave as one coordinated quantum system. These are the conditions where phenomena like superfluidity and Bose-Einstein condensation can appear. Absolute zero is therefore less like a destination and more like a horizon. The closer you get, the stranger matter can become, revealing behaviors that are hidden at everyday warmth. Heat is simply atoms moving faster, on average. When something feels warm, what you are sensing is the busy microscopic motion inside it. In gases, atoms zip around quickly and collide, exchanging energy. In liquids, atoms and molecules slide and tumble past one another in ceaseless motion. In solids, atoms vibrate faster and with greater intensity as heat increases. This is why a hot object can warm a cold one through contact. Faster-moving particles share energy with slower ones until the motion becomes more even. It also explains why temperature is an average. Even in a warm room, some particles are moving faster than others at any moment. You can see this idea in action through Brownian motion, where tiny particles jitter in a fluid because they are being struck from all sides by invisible molecules. Heat is not a substance. It is energy in transit, carried by the motion and collisions of atoms. Sound travels as waves of atomic vibrations through matter. Sound is not a thing that moves through air like a thrown object. It is a traveling pattern of pressure changes passed along as atoms and molecules bump their neighbors. In air, a vibrating speaker pushes nearby molecules together, creating a compression, then leaves a slight rarefaction behind. That push and pull propagates outward as a wave. In solids, atoms are packed more tightly, so the wave can move faster, which is why sound often travels quicker through metal or wood than through air. You can even feel this when a loud bass note makes a surface tremble. Sound needs matter because it is built from coordinated atomic motion. That is why space is silent. There are no atoms between planets to pass the pattern along. Every whispered word, every drumbeat, every thunderclap is a brief choreography of atomic vibrations carrying information through a material medium. Pressure increases when atoms collide more frequently. Pressure is what you feel when countless tiny impacts add up. In a gas, atoms and molecules are constantly striking the walls of their container. Each collision transfers a small impulse, and together they create the steady force we call pressure. If you heat the gas, the particles move faster and collide more energetically, so pressure rises. If you compress the gas into a smaller volume, collisions happen more often, so pressure rises again. This is why a bicycle pump warms as you use it, and why a sealed container can become dangerous if heated. Atmospheric pressure is the same idea on a planetary scale, created by the weight of air and the collisions of its particles all around you. It is easy to forget how physical this is, because you rarely notice it. But your body is built to live inside a constant storm of microscopic impacts, balanced by internal pressure pushing outward in return. Solids hold shape because atoms resist being rearranged. A solid keeps its form because its atoms sit in a stable pattern and strongly resist being moved far from their preferred positions. Think of each atom as resting in a valley of energy, with neighboring atoms acting like springs that pull it back when it is displaced. When you bend a metal paperclip slightly, you are shifting atoms just enough that many return when you release it, which is elastic behavior. If you bend it too far, the atoms slip into a new arrangement, and the change becomes permanent. Different solids behave differently because their atomic bonds differ in strength and geometry. Crystal structures can provide rigidity, while networks and polymers can allow more flexibility. The key idea is that solids are not still. Their atoms vibrate constantly. Yet the overall arrangement remains stable because the forces between atoms create a strong preference for order. Shape is maintained by resistance to rearrangement, not by a lack of motion. Liquids flow because atoms slide past one another. A liquid is an in-between state where atoms and molecules stay close, yet they are not locked into a fixed arrangement. They can move around each other, trading neighbors, reshaping continuously. This is why a liquid can pull, ripple, and take the shape of its container. The ease of that motion varies, and we experience it as viscosity. Honey flows slowly because its molecules tangle and resist sliding. Alcohol flows quickly because its molecules move past one another more easily. Liquids can still support waves and splashes because their particles remain linked by attractions, even while they wander. They also create surface tension, a subtle skin at the boundary where particles are pulled inward more than outward. A liquid is matter with freedom, but not escape. Its atoms are close enough to feel one another, yet loose enough to keep moving, creating flow that looks smooth and effortless. Gases expand because atoms move freely through space. In a gas, atoms and molecules are not bound to a fixed set of neighbors. They travel in straight lines until collisions redirect them, and they spread out to fill whatever space is available. This is why a scent can drift across a room, and why a balloon expands when gas is added. Each particle is in constant motion, and that motion naturally explores the whole container. The expansion feels purposeful, but it is simply probability at work, with countless moving particles sampling every region they can reach. If you reduce the space, collisions become more frequent and pressure rises, which is why gases resist compression. If you increase the temperature, the particles move faster and tend to occupy the space more vigorously. A gas is matter in its most roaming form, defined by freedom of motion. It reminds us that emptiness is never truly empty. If gas is present, it will seek every corner, simply because its atoms are always moving. Chemical reactions occur when atoms rearrange their bonds. Imagine a crowded dance floor where nobody new enters and nobody leaves, but partners keep changing. That is the heart of a chemical reaction. The atoms you start with are still there at the end, yet the connections between them have been reorganized. Those connections, called bonds, are not little hooks. They are shared patterns of electrons that hold atoms together. When conditions are right, old bonds loosen and new ones form, creating substances with different smells, colors, textures, and behaviors. Baking a cake, digesting a meal, and cleaning a stain all depend on this quiet reshuffling. What makes reactions so useful is that they can be guided. Temperature, concentration, and catalysts can steer which bonds are most likely to change. Chemistry is not matter appearing from nowhere. It is atoms switching relationships, and in doing so, rewriting what the material can do. Energy is absorbed or released when atomic bonds change. Bonds are not just connections, they are energy arrangements. To break a bond, you must supply energy, because you are pulling atoms out of a stable relationship. To form a bond, energy is usually released, because the new arrangement sits at a lower energy state. This is why some reactions warm their surroundings, while others cool them. Think of instant cold packs, where a dissolving process pulls energy from your skin, and hand warmers, where a reaction releases heat steadily. The same logic drives cooking, freezing, and even the way your body manages fuel. Energy is not created by the reaction. It is shifted from one form to another, often into motion of particles, which you experience as temperature change. Bond changes are like hills and valleys in an energy landscape. Reactions happen when matter finds a pathway downhill, or when you give it enough push to climb up first. Combustion is a rapid atomic rearrangement involving oxygen. A flame is chemistry moving at high speed. In combustion, atoms from a fuel find oxygen and rearrange into more stable products, releasing energy so quickly that it becomes heat and light. The flicker you see is hot gases rising and turbulent mixing, while the glow comes from energized particles emitting light as they settle. Different fuels burn differently because their structures and impurities affect how easily they break apart and recombine. A candle burns slowly because liquid wax is pulled up a wick, vaporized, and fed to the reaction in a controlled stream. A dry pine needle flashes faster because it offers oxygen many surfaces at once. Combustion also needs the right balance. Too little oxygen, and you get incomplete burning and smoke. Too much cooling, and the reaction cannot sustain itself. Fire feels alive, but it is atoms racing downhill in energy. Rust forms when iron atoms slowly bond with oxygen. Rust is fire's patient cousin. Instead of a bright flame, it is a slow chemical shift that can take days, months, or years. Iron atoms at the surface of a metal object react with oxygen from the air, often helped by water acting as a bridge for charge movement. Over time, the iron transforms into iron oxides, which are brittle and flaky compared to the tough metal beneath. This is why rust can spread and weaken structures, because the new material does not protect the surface well. It can crack, expose fresh iron, and invite more reaction. Salt water speeds the process, which is why coastal environments are hard on cars and ships. Rust is also a reminder that stability is contextual. Iron is useful and strong in many settings, but in the presence of oxygen and moisture, the atomic arrangement it prefers is different. Corrosion is the world gently insisting on change. Photosynthesis rearranges atoms using energy from sunlight. Plants perform a quiet miracle that runs the biosphere. They capture sunlight and use that energy to rearrange atoms into energy-rich molecules. In broad strokes, carbon dioxide and water are transformed into sugars and oxygen. But the real story is a sequence of finely timed steps inside cellular structures. Light excites electrons and special pigments, and that excitement is converted into chemical potential, like charging a tiny battery. That stored energy is then used to build carbon-based molecules, assembling them from simpler pieces. This is not just a way to make food. It is a way to store sunlight in matter. The oxygen released becomes part of the air many organisms depend on, while the sugars become building blocks for wood, fruit, and countless biological materials. Photosynthesis is a bridge between starlight and life, turning photons into chemistry that can be eaten, burned, and woven into ecosystems. Respiration releases energy by reversing photosynthetic chemistry. Your body and most living things run on a controlled return journey. In respiration, energy stored in sugars and other fuels is released in manageable steps. Instead of burning like a flame, cells use a chain of reactions that transfer electrons gradually, capturing energy in forms the cell can spend. Oxygen plays a key role as a final electron acceptor, which is one reason it is so valuable for complex life. The end products are carbon dioxide and water, but along the way, the cell harvests usable energy to power movement, repair, and thought. This is why breathing matters beyond air supply. It supports the chemistry that turns food into function. In essence, respiration is a careful unwrapping of stored energy, not an explosion. The same atoms are involved, but the pathway is designed for life, with membranes, proteins, and gradients acting like a microscopic power plant. Every heartbeat is fueled by this steady chemical bookkeeping. Batteries store energy through controlled atomic reactions. A battery is a chemical system built to be polite. It separates a reaction into two halves and forces electrons to travel the long way around through a circuit where they can do useful work. Inside, different materials have different tendencies to give up or accept electrons. When the battery is connected, atoms at one electrode undergo reactions that release electrons, while atoms at the other electrode take them in. Ions move through an internal pathway called the electrolyte to keep charge balanced. This is why batteries have chemistry and architecture, not just ingredients. Rechargeable batteries work because the reactions can be reversed, pushing ions and electrons back to their starting places when you supply electrical energy. From a phone to an electric car, the principle is the same. The power you feel as light, sound, or motion comes from atoms changing their preferred states, one controlled electron at a time. Catalysts speed reactions by guiding atomic interactions. Sometimes a reaction is possible but reluctant, like two people who would get along if they could only meet in the right moment. A catalyst makes that meeting easier. It provides a pathway that requires less energy to get started, often by holding reactants in just the right positions or by stabilizing a fleeting intermediate state. The catalyst does not get used up in the overall process, which is why small amounts can have large effects. In industry, catalysts are everywhere, shaping fuels, fertilizers, plastics, and pollution control. The catalytic converter in a car, for example, encourages harmful gases to transform into less harmful ones before they leave the exhaust. What is striking is that speed is not only about heat or force. Sometimes it is about guidance. A catalyst is like a careful host at an atomic gathering, arranging introductions that would otherwise happen too slowly to matter. Enzymes are biological catalysts built from precisely arranged atoms. Inside living cells, reactions must happen quickly, cleanly, and at gentle temperatures. Enzymes make that possible. Each enzyme is a folded protein whose shape creates a special pocket, often called an active site, where a reaction is encouraged. The active site is not merely a cavity. Its atoms are arranged to create specific electric fields, subtle attractions, and an orientation that nudges reactants toward transformation. Many enzymes are also selective, meaning they work on one kind of molecule and ignore others, which keeps cellular chemistry from turning into chaos. This precision allows life to build complex molecules, break down nutrients, copy genetic material, and manage energy, all in watery conditions that would otherwise be too slow. Enzymes are also adjustable. Their activity can be turned up or down, helping cells respond to hunger, stress, or growth. In a sense, enzymes are molecular tools, and their craftsmanship is written in atomic placement. Life depends on atoms reacting reliably under gentle conditions. A living cell is not a violent environment. It is mostly water, modest temperatures, and soft materials. Yet within that calm, thousands of reactions happen every second, coordinated like a city at night. Life depends on chemistry that is both dependable and controllable. Reactions must proceed without random explosions, and they must be steerable towards specific products. This is why biological chemistry relies on gradual steps, compartments, membranes, and molecular helpers. It is also why certain elements are so central. Carbon forms stable frameworks, oxygen helps manage energy transfer, and phosphorus builds energy currency and structural backbones. Reliability matters because errors accumulate. A single reaction going wrong can damage a molecule, which can damage a process, which can threaten a cell. Life thrives because atomic behavior is consistent enough to build systems on top of it. Evolution did not invent new physics. It learned to choreograph existing atomic rules into metabolism, growth, repair, and reproduction. Some atoms are radioactive because their nuclei are unstable. Radioactivity begins when a nucleus is built in a way that cannot stay comfortable forever. The balance between protons and neutrons matters, and for some combinations, the internal forces never settle into long-term peace. Nature responds by seeking a more stable arrangement, and the nucleus eventually changes on its own. This is not a chemical mood swing. It is a deeper shift in the heart of the atom. Some unstable nuclei change quickly, while others linger for ages, quietly ticking away. What makes radioactivity so fascinating is that it is both predictable and unpredictable. We can measure an average pace for a large sample, yet we cannot point to a single atom and say when it will transform. In the ground beneath you, in certain rocks, and even in small traces in food and air, these unstable atoms exist naturally. Radioactivity is not only a human invention, it is part of how matter behaves when its internal architecture is slightly out of balance. Radioactive decay transforms atoms into entirely different elements. In everyday chemistry, atoms rearrange their bonds but keep their identities. In radioactive decay, identity itself can change. When a nucleus emits a particle or reorganizes internally, the number of protons may change, and that means the element changes. One atom becomes another, without any outside trigger needed. This is an ancient idea that once sounded like alchemy, yet nature performs it routinely. In a sample of a radioactive element, each decay event is like a quiet act of transmutation. Over time, a chain of changes can occur, stepping through several different elements before reaching a stable endpoint. This is how some rocks gradually accumulate new atoms inside their crystal lattices, storing a record of internal change. It is also why radioactive materials must be handled carefully. They are not static substances. They are substances in the middle of becoming something else, releasing energy and particles as they go. Decay is the universe rewriting its own labels. Alpha decay releases helium nuclei from heavy atoms. Alpha decay is one of nature's elegant ways of shedding excess nuclear weight. A heavy nucleus can become more stable by ejecting a compact bundle made of 2 protons and 2 neutrons. That bundle is an alpha particle, and it is essentially the nucleus of a helium atom. When it flies out, the original nucleus becomes a different element because it has lost 2 protons. The mass drops, the identity shifts, and the nucleus steps closer to stability. Alpha particles do not travel very far in air, and they can be stopped by something as thin as paper. Yet inside matter they can cause intense local effects because they carry significant charge. Their short range is part of why containment works so well, and also why internal exposure can be dangerous. Alpha decay is a reminder that nuclear change can be both gentle in reach and profound in consequence, turning one element into another while releasing a helium nucleus as a tiny messenger. Beta decay converts neutrons into protons or electrons. Beta decay is a kind of internal rebalancing act. In one common form, a neutron inside the nucleus transforms into a proton, and in the process, it emits an electron, along with an elusive particle called a neutrino. That single change increases the proton count by 1, which means the atom becomes a new element. In another form, a proton can convert into a neutron with a different kind of emitted particle. The details are subtle, but the outcome is clear. Beta decay is how a nucleus adjusts its proton-to-neutron ratio when it is out of balance. Beta particles can travel farther than alpha particles, and they can pass through thin materials, which is why shielding needs to be more considered. In nature, beta decay contributes to the slow transformation of radioactive series, and in science, it helped reveal that particles can change identity in ways that feel almost like a magic trick. A neutron becoming a proton is not chemistry. It is the nucleus rewriting itself from within. Gamma radiation releases pure energy from atomic nuclei. Sometimes a nucleus does not need to change its element to release energy. It can simply drop from a higher energy state to a lower one and emit that difference as gamma radiation. Gamma rays are not particles of matter. They are packets of electromagnetic energy, like light, but far more energetic. Because they carry no electric charge and have very short wavelengths, they can pass through materials that would easily stop alpha or beta particles. That penetrating power is why gamma radiation is both useful and hazardous. It can be used to image internal processes, sterilize equipment, and treat certain diseases when applied carefully. But it also requires serious shielding and respect. Gamma emission is often the finishing touch after another kind of decay, like a nucleus exhaling its last leftover excitement. It is a reminder that nuclei have energy levels too, and that they can release energy in a pure, focused form. When a nucleus emits gamma rays, it is not throwing out a piece of itself. It is releasing a burst of stored energy, like a bell ringing without a visible striker. Nuclear fission splits heavy atoms into lighter ones. In fission, a heavy nucleus breaks apart into 2 smaller nuclei, along with extra neutrons and a great deal of energy. The reason it can be so energetic is that the fragments can be more tightly bound than the original heavy nucleus, and the difference emerges as released energy. In some materials, incoming neutrons can trigger fission, and the emitted neutrons can trigger more fissions, creating a chain reaction. In a controlled setting, this chain reaction can be managed to produce steady heat, which can then generate electricity. In an uncontrolled setting, it can release energy very rapidly. What makes fission feel dramatic is that it takes something tiny and makes it consequential on a human scale. It also produces a mix of new atoms that can themselves be radioactive, which is part of why fission must be handled with careful planning. Fission shows that the nucleus is not just dense. It is an energy reservoir, and under the right conditions, it can be unlocked by splitting a single heavy atom into smaller pieces. Nuclear fusion joins light atoms into heavier ones. Fusion is the opposite approach to nuclear change. Instead of splitting something heavy, it pushes light nuclei together until they combine into a heavier nucleus. This requires extreme conditions because positively charged nuclei repel each other strongly. Only at very high temperatures and pressures do they get close enough for the strong nuclear force to take over and bind them. When fusion happens, it can release enormous energy because the resulting nucleus can be more stable than the starting ones. Fusion is especially potent with the lightest elements, which is why it is central to the universe's power supply. On Earth, fusion research aims to create a controlled version of the process that stars perform naturally. It is difficult because the same conditions that make fusion possible also make it hard to contain. But the promise is compelling, a process that produces vast energy from small amounts of fuel. Fusion is nature's way of building heavier nuclei from simple beginnings, like a cosmic assembly line that runs on pressure, heat, and time. Fusion powers stars by converting mass into energy. A star shines because its core is a place where nuclei meet under crushing pressure. In that furnace, light atoms fuse into heavier ones, and a small amount of mass is converted into energy. That energy begins as high-energy radiation in the core and takes a long, slow journey outward, being absorbed and re-emitted countless times. Eventually, it escapes as the light and warmth that travel through space. The star's outward glow is balanced by gravity pulling inward, creating a steady, long-lived stability. When fusion slows or shifts, the entire life of the star changes. That is why different stars age differently, and why the sky contains stars in many stages of life. What is astonishing is that the sunlight on your skin began as nuclear bookkeeping deep in the sun, where a small mass difference became radiant energy. Stars are not burning wood or oil. They are converting a fraction of matter into light, and they can do it for billions of years. The sun transforms hydrogen atoms into helium continuously. At the center of the sun, hydrogen nuclei are packed so densely and heated so intensely that fusion becomes possible. Through a sequence of steps, hydrogen nuclei ultimately combine to form helium, and in the process, energy is released. This is not a simple one-step collision. It is a pathway that includes intermediate stages and delicate probabilities, which is one reason the sun burns steadily rather than explosively. The energy produced supports the sun against gravitational collapse and powers its enduring light. The sunlight that reaches Earth today began deep inside the sun long ago, starting as energy released during fusion, then slowly working its way outward. By the time it arrives here, it has become the gentle illumination that warms oceans and drives winds. The sun is therefore not merely a bright object in the sky. It is a continuous fusion reactor, turning hydrogen into helium and turning mass into the energy that makes days possible. Every heavier element was forged inside stars or explosions. Hydrogen and helium dominated the early universe, but the elements that make rocky worlds and living bodies required a longer story. Inside stars, fusion can build elements up to a certain point, producing atoms like carbon, oxygen, and silicon as stars mature. But the heaviest elements need more extreme moments. When massive stars die in powerful explosions, or when dense stellar remnants collide, conditions become intense enough to create and scatter very heavy nuclei. Those events seed space with new atoms that later become part of planets, mountains, and eventually living cells. This is why the periodic table is also a history book. It tells a story of cosmic manufacturing, where different environments forge different atoms. The gold in jewelry, the iodine in the human body, and the uranium in rocks are not accidental. They are the outcome of rare astrophysical events, preserved in matter and carried across time. Every heavy element is a souvenir from a star's life, or from a star's most dramatic ending. Some atoms are radioactive because their nuclei are unstable. Radioactivity begins when a nucleus is built in a way that cannot stay comfortable forever. The balance between protons and neutrons matters, and for some combinations, the internal forces never settle into long-term peace. Nature responds by seeking a more stable arrangement, and the nucleus eventually changes on its own. This is not a chemical mood swing. It is a deeper shift in the heart of the atom. Some unstable nuclei change quickly, while others linger for ages, quietly ticking away. What makes radioactivity so fascinating is that it is both predictable and unpredictable. We can measure an average pace for a large sample, yet we cannot point to a single atom and say when it will transform. In the ground beneath you, in certain rocks, and even in small traces in food and air, these unstable atoms exist naturally. Radioactivity is not only a human invention. It is part of how matter behaves when its internal architecture is slightly out of balance. Radioactive decay transforms atoms into entirely different elements. In everyday chemistry, atoms rearrange their bonds but keep their identities. In radioactive decay, identity itself can change. When a nucleus emits a particle or reorganizes internally, the number of protons may change, and that means the element changes. One atom becomes another, without any outside trigger needed. This is an ancient idea that once sounded like alchemy, yet nature performs it routinely. In a sample of a radioactive element, each decay event is like a quiet act of transmutation. Over time, a chain of changes can occur, stepping through several different elements before reaching a stable endpoint. This is how some rocks gradually accumulate new atoms inside their crystal lattices, storing a record of internal change. It is also why radioactive materials must be handled carefully. They are not static substances. They are substances in the middle of becoming something else, releasing energy and particles as they go. Decay is the universe rewriting its own labels. Alpha decay releases helium nuclei from heavy atoms. Alpha decay is one of nature's elegant ways of shedding excess nuclear weight. A heavy nucleus can become more stable by ejecting a compact bundle made of 2 protons and 2 neutrons. That bundle is an alpha particle, and it is essentially the nucleus of a helium atom. When it flies out, the original nucleus becomes a different element. Because it has lost 2 protons. The mass drops, the identity shifts, and the nucleus steps closer to stability. Alpha particles do not travel very far in air, and they can be stopped by something as thin as paper. Yet inside matter, they can cause intense local effects because they carry significant charge. Their short range is part of why containment works so well, and also why internal exposure can be dangerous. Alpha decay is a reminder that nuclear change can be both gentle in reach and profound in consequence, turning one element into another while releasing a helium nucleus as a tiny messenger. Beta decay converts neutrons into protons or electrons. Beta decay is a kind of internal rebalancing act. In one common form, a neutron inside the nucleus transforms into a proton, and in the process, it emits an electron, along with an elusive particle called a neutrino. That single change increases the proton count by 1, which means the atom becomes a new element. In another form, a proton can convert into a neutron with a different kind of emitted particle. The details are subtle, but the outcome is clear. Beta decay is how a nucleus adjusts its proton-to-neutron ratio when it is out of balance. Beta particles can travel farther than alpha particles, and they can pass through thin materials, which is why shielding needs to be more considered. In nature, beta decay contributes to the slow transformation of radioactive series, and in science, it helped reveal that particles can change identity in ways that feel almost like a magic trick. A neutron becoming a proton is not chemistry. It is the nucleus rewriting itself from within. Gamma radiation releases pure energy from atomic nuclei. Sometimes a nucleus does not need to change its element to release energy. It can simply drop from a higher energy state to a lower one and emit that difference as gamma radiation. Gamma rays are not particles of matter. They are packets of electromagnetic energy, like light, but far more energetic. Because they carry no electric charge and have very short wavelengths, they can pass through materials that would easily stop alpha or beta particles. That penetrating power is why gamma radiation is both useful and hazardous. It can be used to image internal processes, sterilize equipment, and treat certain diseases when applied carefully. But it also requires serious shielding and respect. Gamma emission is often the finishing touch after another kind of decay, like a nucleus exhaling its last leftover excitement. It is a reminder that nuclei have energy levels too, and that they can release energy in a pure, focused form. When a nucleus emits gamma rays, it is not throwing out a piece of itself. It is releasing a burst of stored energy, like a bell ringing without a visible striker. Nuclear fission splits heavy atoms into lighter ones. In fission, a heavy nucleus breaks apart into two smaller nuclei, along with extra neutrons and a great deal of energy. The reason it can be so energetic is that the fragments can be more tightly bound than the original heavy nucleus, and the difference emerges as released energy. In some materials, incoming neutrons can trigger fission, and the emitted neutrons can trigger more fissions, creating a chain reaction. In the controlled setting, this chain reaction can be managed to produce steady heat, which can then generate electricity. In an uncontrolled setting, it can release energy very rapidly. What makes fission feel dramatic is that it takes something tiny and makes it consequential on a human scale. It also produces a mix of new atoms that can themselves be radioactive, which is part of why fission must be handled with careful planning. Fission shows that the nucleus is not just dense. It is an energy reservoir, and under the right conditions, it can be unlocked by splitting a single heavy atom into smaller pieces. Nuclear fusion joins light atoms into heavier ones. Fusion is the opposite approach to nuclear change. Instead of splitting something heavy, it pushes light nuclei together until they combine into a heavier nucleus. This requires extreme conditions, because positively charged nuclei repel each other strongly. Only at very high temperatures and pressures do they get close enough for the strong nuclear force to take over and bind them. When fusion happens, it can release enormous energy, because the resulting nucleus can be more stable than the starting ones. Fusion is especially potent with the lightest elements, which is why it is central to the universe's power supply. On Earth, fusion research aims to create a controlled version of the process that stars perform naturally. It is difficult because the same conditions that make fusion possible also make it hard to contain. But the promise is compelling, a process that produces vast energy from small amounts of fuel. Fusion is nature's way of building heavier nuclei from simple beginnings, like a cosmic assembly line that runs on pressure, heat, and time. Fusion powers stars by converting mass into energy. A star shines because its core is a place where nuclei meet under crushing pressure. In that furnace, light atoms fuse into heavier ones, and a small amount of mass is converted into energy. That energy begins as high-energy radiation in the core and takes a long, slow journey outward, being absorbed and re-emitted countless times. Eventually it escapes as the light and warmth that travel through space. The star's outward glow is balanced by gravity pulling inward, creating a steady, long-lived stability. When fusion slows or shifts, the entire life of the star changes. That is why different stars age differently, and why the sky contains stars in many stages of life. What is astonishing is that the sunlight on your skin began as nuclear bookkeeping deep in the sun, where a small mass difference became radiant energy. Stars are not burning wood or oil. They are converting a fraction of matter into light, and they can do it for billions of years. The sun transforms hydrogen atoms into helium continuously. At the center of the sun, hydrogen nuclei are packed so densely and heated so intensely that fusion becomes possible. Through a sequence of steps, hydrogen nuclei ultimately combine to form helium, and in the process, energy is released. This is not a simple one-step collision. It is a pathway that includes intermediate stages and delicate probabilities, which is one reason the sun burns steadily rather than explosively. The energy produced supports the sun against gravitational collapse and powers its enduring light. The sunlight that reaches Earth today began deep inside the sun long ago, starting as energy released during fusion, then slowly working its way outward. By the time it arrives here, it has become the gentle illumination that warms oceans and drives winds. The sun is therefore not merely a bright object in the sky. It is a continuous fusion reactor, turning hydrogen into helium and turning mass into the energy that makes days possible. Every heavier element was forged inside stars or explosions. Hydrogen and helium dominated the early universe, but the elements that make rocky worlds and living bodies required a longer story. Inside stars, fusion can build elements up to a certain point, producing atoms like carbon, oxygen, and silicon as stars mature. But the heaviest elements need more extreme moments. When massive stars die in powerful explosions, or when dense stellar remnants collide, conditions become intense enough to create and scatter very heavy nuclei. Those events seed space with new atoms that later become part of planets, mountains, and eventually living cells. This is why the periodic table is also a history book. It tells a story of cosmic manufacturing, where different environments forge different atoms. The gold in jewelry, the iodine in the human body, and the uranium in rocks are not accidental. They are the outcome of rare astrophysical events, preserved in matter and carried across time. Every heavy element is a souvenir from a star's life, or from a star's most dramatic ending. Supernova scatter newly formed atoms across the universe. A supernova is not only an ending, it is a cosmic delivery system. In the final moments of a massive star, the explosion can outshine entire galaxies, and the shockwave hurls matter outward at extraordinary speeds. Atoms that were built and stored inside the star are suddenly flung into surrounding space, mixing into clouds of gas and dust. That expanding debris becomes raw material for future stars, planets, and chemistry. You can think of it as the universe's way of sharing its inventory, taking what was once locked in a single star and distributing it widely. The blast also creates conditions so extreme that additional heavy nuclei can form in the chaos, adding new ingredients to the mix. Over time, that enriched material drifts, cools, and gathers again. Supernova are how the universe refuses to keep its most interesting atoms to itself. Some atoms on Earth predate the solar system itself. Not every atom on Earth was born in the same neighborhood. A small fraction arrived as ancient travelers, formed long before the Sun existed. These atoms wandered through interstellar space inside grains of dust, surviving the cold, radiation, and collisions of a restless galaxy. When the cloud that formed our solar system collapsed, those grains were swept in, becoming part of the swirling disk that built planets. Most material was heated and mixed, but some tiny grains preserved their original isotopic fingerprints, like cosmic passports that still carry their old stamps. Scientists can find these presolar grains in certain meteorites, where they were sheltered from Earth's recycling processes. Holding such a grain is like holding a fragment of a time before Earth, before the Sun, before familiar orbits. It is a reminder that our planet is not made only of local history. It contains a few quiet survivors from a far older chapter. Cosmic rays occasionally alter atoms high in the atmosphere. Earth is constantly being brushed by particles from space, some traveling at astonishing energies. When these cosmic rays strike the upper atmosphere, they collide with atoms there and create cascades of new particles. Those cascades can knock neutrons into nuclei, subtly changing them into different isotopes. This process produces rare atoms that become useful markers for scientists because they can be tracked as they fall through the atmosphere and enter natural cycles. It is also a reminder that the sky is not a sealed roof. Space and Earth interact, and that interaction leaves chemical traces. The changes are typically tiny and spread out, not something you feel day to day, but they are real. They can be measured in air, ice, and even in living tissues. In a sense, the atmosphere is a gentle laboratory that runs continuously, with cosmic rays as its invisible input. Atoms drift through space as dust between stars. Between stars, space is not perfectly empty. It contains thin clouds of gas and dust, and those dust grains are built from atoms bound into tiny solids. Some grains are silicate-rich, others contain carbon-based material, and many are coated with simple ices in colder regions. Over long times, these grains drift, collide, stick, and sometimes break apart again. They can absorb and scatter starlight, shaping how galaxies look through telescopes. They can also provide surfaces where simple molecules form more easily than they would in open gas. In the dark spaces between stars, dust becomes a quiet meeting place for atoms, helping them gather into larger chemical possibilities. You might imagine it as a slow snowfall in space, except the flakes are microscopic, and the storm lasts for millions of years. These drifting atoms, riding on dust, are part of the supply chain of future worlds. Interstellar clouds collapse as atoms slowly gather together. A cloud of gas in space can drift for ages without changing much, until gravity begins to win. When a region becomes dense enough, it starts pulling more strongly on itself, and the collapse slowly accelerates. As atoms and molecules fall inward, the cloud fragments into clumps, and those clumps can become the seeds of new stars. As the material compresses, it heats up, and the growing warmth changes the chemistry inside the cloud. Molecules break, reform, and sometimes build into more complex compounds in sheltered pockets. Meanwhile, dust grains provide extra help, acting like tiny scaffolds where atoms can meet and stick. The collapse is not a sudden crash. It is a drawn-out gathering, a slow tightening of a vast cold structure into something bright and concentrated. Every star begins as atoms that were once far apart, gradually persuaded by gravity to become close enough to ignite a new light. Planets form when atoms clump under gravity. Before there were planets, there was a disk of gas and dust circling a young star. Inside that disk, atoms bonded into grains, grains stuck into pebbles, and pebbles grew into larger bodies through repeated collisions. Gravity then took over, helping these growing chunks sweep up more material along their paths. Some became rocky worlds, built from heavier elements that could survive close to the star. Others became gas giants farther out, where lighter gases could remain and gather into thick envelopes. This process is messy, with impacts, melting, and rebuilding, but it is guided by simple rules. Matter attracts matter, and over time, small differences in mass can snowball into major structures. A planet is therefore not a single object so much as a history of accumulation shaped by countless atomic meetings. Worlds are made from dust that learned to stick, and from gravity that refused to let go. Earth's atmosphere exists because atoms were captured and retained. An atmosphere is a balancing act between supply and escape. Early Earth gathered gases from multiple sources, including material released from the interior and impacts from space. Over time, gravity helped keep many of those atoms close, but lighter gases could more easily drift away, especially under the sun's energetic influence. What remained depended on chemistry, temperature, and the protective effects of Earth's magnetic field and growing complexity. Some gases were locked into rocks and oceans, while others accumulated in the air. The atmosphere we live in now is not simply a leftover. It is a shape system, built and adjusted over geological time. Its composition influences climate, protects the surface from harsh radiation, and provides the ingredients for breathing and weather. When you look up at the sky, you are seeing a layer of captured atoms that Earth managed to hold onto, making the surface gentle enough for life to thrive. Life rearranges atoms but never creates or destroys them. Living things can feel miraculous, but they still obey a quiet accounting rule. In ordinary biological processes, atoms are not created from nothing, and they do not vanish into nothing. Instead, life borrows atoms, rearranges them into useful molecules, and releases them again. A plant takes in carbon dioxide and water and builds sugars and fibers. An animal eats those molecules, breaks them apart, and uses the pieces to build muscle, hormones, and heat. Microbes decompose what remains, returning atoms to soil and air. Life is a choreography of rearrangement, not a violation of conservation. This is why ecosystems can be understood as cycles rather than one-way streams. It is also why choices matter. The atoms will continue, but the forms they take and the paths they travel depend on how living systems interact. Life is a temporary pattern written in matter that persists. Atoms cycle endlessly through air, water, soil, and living things. Picture an atom of nitrogen drifting in the air, then being fixed by microbes into a form plants can use. Later it becomes part of a leaf, then part of an animal that eats that leaf, then returns to the soil through waste or decay. Or imagine a carbon atom moving from air into a tree, then into wood, then into smoke, and back into the atmosphere again. These cycles can be fast or slow, depending on where the atom is stored. Some loops happen in days, while others take centuries or longer. The important thing is that Earth is not a set of separate compartments. Air, oceans, rocks, and life exchange atoms constantly. This exchange is what makes the planet feel alive and connected. When we change one part of the system, the movement of atoms changes too, sometimes in ways that take time to notice. The cycles continue, patient and persistent, carrying matter through countless forms. The atoms you breathe today once belonged to ancient organisms. Breathing feels like something that happens only in the present, but the atoms in each inhale carry deep history. Oxygen atoms may have once been part of a fern, a plankton bloom, or a long-vanished forest. Carbon atoms in the air may have passed through many lungs and leaves over time, cycling through bodies and landscapes. Because gases mix across the planet, the atmosphere becomes a shared reservoir, where atoms are continuously traded among living things. That means each breath is not only personal. It is part of a long communal circulation. The thought can make the air feel newly intimate. The atmosphere holds traces of countless lives, not as memories you can read, but as matter that has traveled through many forms. When you exhale, you return atoms to that shared pool, where they will continue their journeys. Breathing is a connection to the past, carried in the simplest act of the present. Atomic clocks keep time by measuring precise energy transitions. Some clocks count swinging pendulums or vibrating crystals, but the most accurate clocks listen to atoms. Certain atoms switch between two energy states at a perfectly consistent frequency, like a note that never drifts out of tune. In an atomic clock, scientists use microwaves to nudge atoms and find the exact frequency that matches that transition. When the match is perfect, the atoms respond, and the clock locks onto that rhythm. This is not a mechanical tick. It is a quantum heartbeat, repeated with astonishing stability. Over long periods, this steadiness keeps time far better than ordinary methods, which can be nudged by temperature, wear, or tiny imperfections. Atomic timekeeping becomes the backbone for systems that demand absolute precision. It is remarkable to realize that the most reliable seconds humans can measure are defined by atoms changing energy state, again and again, with unwavering consistency. Modern navigation relies on atomic timing accuracy. When you use satellite navigation, your phone is not directly measuring distance with a ruler. It is measuring time. Satellites broadcast signals stamped with precise timestamps, and your receiver compares when those signals arrive. Because radio waves travel at the speed of light, even a tiny timing error becomes a large position error. A few billionths of a second can translate into meters on the ground. That is why satellites carry atomic clocks, so their timestamps stay aligned. The system then uses several satellites at once to solve where you must be, based on the pattern of arrival times. It is a beautiful example of hidden physics in daily life. Directions to a cafe depend on atomic transitions happening reliably in orbit. Even Earth's gravity and motion introduce timing shifts that must be corrected for accuracy. Navigation feels like a map, but beneath it is a network of clocks, all kept honest by atoms that refuse to drift. Semiconductors work because atoms control electron movement precisely. Semiconductors are materials that can behave like conductors or insulators depending on how they are prepared. Their secret lies in how electrons are allowed to move through the atomic structure. In a semiconductor crystal, electrons occupy energy bands, and a small push of energy can let them flow. By adding tiny amounts of impurity atoms, a process called doping, engineers can create regions with extra mobile electrons, or regions with missing electrons that act like positive carriers. When these regions meet, they form junctions that control current like a gate. This ability to guide electrons, not merely allow or block them, is what makes modern electronics possible. It is astonishingly delicate. A few atoms among millions can change behavior dramatically. Your devices rely on materials where atomic structure is tuned so carefully that electrons can be invited to move, stopped, or redirected on command. Computer chips depend on carefully arranged atomic layers. A microchip is less like a single object and more like a carefully layered landscape. Thin films of different materials are deposited, patterned, and etched to create billions of tiny components. These layers can be only a few atoms thick, which means the boundary between materials matters immensely. A slight defect, a stray atom, or a microscopic crack can change how a transistor behaves. That is why chip fabrication happens in clean rooms where even dust is a threat, because a speck can be enormous compared to the structures being made. The manufacturing process is a kind of atomic choreography, using light, chemistry, and precise timing to build patterns too small to see directly. The result is a device that turns electron flow into logic, memory, images, and sound. When you stream a video or record your voice, you are relying on stacked atomic layers holding their places. Modern computing is matter arranged with extraordinary discipline. Medical imaging uses atomic behavior to reveal internal structures. Many medical images are made possible because atoms respond predictably to energy. In magnetic resonance imaging, hydrogen nuclei in water and fat behave like tiny magnets. In a strong magnetic field, they align, and when nudged by radio waves, they emit signals as they relax back. Those signals vary by tissue type, allowing detailed pictures without cutting the body open. In other imaging methods, detectors capture how high energy photons pass through the body, revealing denser structures like bone. These techniques work because atomic scale interactions shape what the detectors receive. The human body becomes readable by how its atoms absorb, emit, or influence energy. It is a gentle kind of seeing. You are not viewing organs directly, but translating atomic behavior into a map of anatomy. Medical imaging turns the invisible into information. It is one of the most humane uses of physics, letting doctors look inside while leaving the skin untouched. Radiation therapy targets rapidly dividing cells at the atomic scale. Cancer treatments often depend on a vulnerability. Rapidly dividing cells must copy their genetic material frequently, and that process can be disrupted. Radiation therapy uses carefully aimed energy to damage DNA inside targeted tissue. The damage occurs through atomic scale interactions, such as ionization, where electrons are knocked loose and molecules become reactive. Those reactions can break chemical bonds in DNA, making it harder for cells to reproduce correctly. Healthy tissue can be affected too, which is why treatment planning is so precise, balancing dose, angle, and timing. Modern techniques shape beams and use imaging guidance to concentrate effects where they are needed most. It is both powerful and delicate. The goal is not destruction for its own sake, but a controlled interruption of harmful growth. Radiation therapy is a reminder that life depends on molecular integrity, and that carefully delivered energy can change outcomes by altering atoms and bonds in the right place. Nanotechnology manipulates matter atom by atom. Nanotechnology operates in a realm where a small change can have outsized effects. At these scales, surface area becomes enormous relative to volume, and materials can behave differently than they do in bulk. Scientists can engineer nanoparticles that catalyze reactions, deliver drugs, or alter optical properties. Some nanostructures are built with patterns so fine that they interact with light in unusual ways, creating colors without pigments. Others are designed to strengthen materials by providing reinforcement at tiny scales. The phrase atom by atom is not always literal, but the ambition is to control structure with near atomic precision. This is how new possibilities emerge. Matter becomes something you can design, not just use. It also demands care, because small particles can move through environments and bodies in unexpected ways. Nanotechnology is a frontier where chemistry, physics, and engineering meet, and where the smallest arrangements can reshape what materials can do. Some materials are engineered with atomic-level precision. In advanced materials science, the goal is not merely to mix ingredients, but to place atoms in deliberate patterns. By controlling composition layer by layer, scientists can create materials with properties that do not occur naturally. Superlattices, for example, combine thin layers of different crystals so electrons experience a designed landscape. This can alter conductivity, magnetism, or optical response. In other cases, atoms are arranged to create pores of uniform size, allowing selective filtering at molecular scales. Even strength can be engineered by tuning grain boundaries and atomic defects, turning weaknesses into controlled features. The result is a new kind of craftsmanship. Instead of carving wood or forging metal, researchers shape the arrangement of matter itself. It is a slow, precise art, backed by powerful tools. The most exciting part is that a material's behavior can be planned from its structure, meaning we can imagine the property first, then build the atomic arrangement that produces it. Future technologies may rely on quantum atomic behavior. Some emerging technologies aim to use the strangeness of atoms rather than fight it. Quantum devices may exploit superposition and entanglement, while particles share linked states across distance. In quantum computing, information can be stored in quantum states that allow certain problems to be approached in new ways. In quantum sensing, tiny shifts in atomic states can detect extremely weak signals, such as subtle magnetic fields or minute changes in gravity. Quantum communication may use atomic and photonic states to create secure links that reveal tampering. These ideas are challenging because quantum states are fragile and easily disturbed by the environment. Yet progress continues because the payoff could be profound. It is a different style of engineering, one that must respect probability and coherence rather than simple on and off switches. The future may include devices that feel almost like science fiction, yet their foundations are already present in the behavior of individual atoms. Understanding atoms allows humans to reshape the material world. Once we understood that matter is built from atoms and bonds, we gained a new kind of leverage. We could predict reactions, create new compounds, and refine materials with intention rather than trial and error alone. This knowledge made fertilizers that feed billions, medicines that target specific pathways, and alloys that resist heat and corrosion. It enabled electronics, clean energy technologies, and new ways of storing and transmitting information. It also carries responsibility, because the ability to reshape matter includes the ability to create hazards, pollution, and powerful weapons. Understanding brings choice, and choice brings ethics. The deepest wonder is that the same atomic rules apply everywhere, from a kitchen to a laboratory to a distant star. By learning those rules, humans learn to cooperate with nature's patterns. We cannot break the laws of physics, but we can work within them, creatively. In that sense, atomic knowledge is not just science. It is a toolkit for building futures. Atoms obey simple rules that lead to extraordinary complexity. At the level of atoms, the rules are surprisingly few. Charges attract or repel, energy prefers lower states, and certain arrangements are allowed while others are not. Yet when you repeat those rules across vast numbers of atoms, complexity blooms. A handful of elements can assemble into salt crystals, tree bark, ocean foam, and neural tissue simply because the same basic interactions play out in different patterns. It is a little like music. A small set of notes can create lullabies, symphonies, and jazz, depending on how they are arranged. In matter, the notes are atoms and bonds, and the melodies are structures and reactions. Complexity is not added from outside. It emerges from repetition and scale. That is one of the deepest comforts in science. The universe does not need endless special rules to make wonders. Simple rules, applied patiently, are enough. Small atomic changes can create dramatically different substances. Sometimes the smallest shift creates a completely new world of behavior. Swap one atom in a molecule, and a scent can change from sweet to sharp. Move a few atoms within a crystal, and the material can become harder, softer, clearer, or darker. Even in metals, a tiny change in composition can alter strength, flexibility, or resistance to corrosion. This is why materials science can feel like a careful kind of spellcraft. The ingredients may seem nearly the same, yet the outcome can be startlingly different. Nature is sensitive to detail because atoms interact locally. A small change can cascade through a structure, changing how vibrations travel, how electrons move, or how molecules fit together. It is also why biology is so powerful. A single change in a molecular building block can influence how a protein folds, which can change how a cell behaves. In the atomic world, tiny edits can rewrite the whole story. The universe's diversity arises from a limited set of atoms. It is easy to assume the universe must contain an endless catalogue of ingredients to create so many different things. In reality, the number of stable elements is limited, and yet the combinations are effectively boundless. The diversity comes from arrangement, proportion, and environment. Carbon can form chains, rings, sheets, and lattices. Silicon and oxygen can build sprawling mineral frameworks. Hydrogen can be part of water, acids, fuels, and the chemistry of stars. When you vary temperature and pressure, the same atoms adopt new structures and new behaviors. Diversity, then, is not only about what you have. It is about how you use it. That idea echoes everywhere, from cooking to architecture to music. The cosmos builds with a modest palette, then explores it creatively across billions of years. The result is a universe that feels endlessly varied, even though the underlying pieces are familiar and few. Atoms follow probabilities rather than certainties at tiny scales. At everyday scales, we expect definite answers. A ball is here, then it is there. But at atomic scales, nature often offers probabilities instead. An electron is described by where it is likely to be found, not by a single guaranteed location. Outcomes in experiments can be predicted statistically with great accuracy, yet individual events remain uncertain. That uncertainty is not a flaw in our instruments. It is part of how the world works when it is very small. This changes the flavor of reality. It means that prediction becomes a matter of distributions, not single paths. Strangely, this probabilistic behavior can still produce stable results at larger scales, because countless tiny uncertainties average out into reliable patterns. Your chair does not dissolve into chance. Yet the atomic foundation beneath it is governed by likelihood. The world is solid and dependable, built on rules that are softly statistical at the bottom. It is one of nature's most beautiful contradictions. Observation itself can influence atomic outcomes. In the atomic world, measuring is not like quietly watching from a distance. To measure something, you must interact with it, and that interaction can change what happens next. In classic experiments, attempts to determine which path a particle takes can erase the interference pattern that appears when paths remain unmeasured. This is not because a human mind is magical. It is because measurement requires a physical exchange of information, and that exchange alters the system. The boundary between system and observer becomes part of the story. That idea can feel unsettling at first, as if reality is shy. But it is also empowering. It means the tools we use matter, and the questions we ask shape what can be known. Atoms respond to interactions. not to intentions. Still, the lesson remains. At tiny scales, knowledge is not free. The act of finding out can leave footprints, and the footprints can redirect the outcome. The atomic world behaves differently than everyday experience suggests. Your intuition was trained on objects that are large, slow, and warm. Atoms live in a different regime. They can tunnel through barriers they do not have enough energy to climb, simply because quantum rules allow a small chance of passage. They can act as waves in some situations and as particles in others, depending on how they are probed. They can occupy discrete energy states rather than sliding smoothly through all possible values. None of this shows up in daily life because the effects are usually drowned out by scale and noise. But the rules are always there, quietly governing chemistry, light, and the stability of matter. Learning about atoms is like learning that the floor beneath your house is built on a different geometry than you imagined. The house still stands. It just stands on deeper principles. The atomic world asks you to loosen your grip on everyday expectations and accept a stranger, more elegant foundation. Atoms connect physics, chemistry, biology, and astronomy seamlessly. Atoms are the common language that lets the sciences speak to one another. Physics describes the forces and quantum rules that shape atomic behavior. Chemistry explores how atoms bond, react, and form materials. Biology builds life from those reactions, using molecular machinery to store information and manage energy. Astronomy reads atomic signatures in starlight to learn what distant worlds are made of. These fields can sound separate, but atoms stitch them together. A stellar spectrum and a blood cell are linked by the same underlying ingredients and rules. When you understand atoms, you start to see bridges everywhere. The glow of a neon sign, the scent of a flower, the strength of bone, and the birth of planets all become chapters in one story. That story is not only intellectual, it is comforting. It suggests the universe is coherent, not fragmented. Different scales, different phenomena, one set of building blocks. Atoms are the thread. Learning about atoms reveals the hidden structure of reality. So much of life is lived at the surface of things. We notice texture, taste, sound, color, and weight, and we treat them as basic. But when you learn about atoms, those qualities become explanations rather than mysteries. Texture becomes forces and structure. Taste becomes molecular interactions. Color becomes selective absorption and emission. Even the shape of a crystal becomes a repeated pattern that can be described and predicted. The world begins to feel less like a collection of separate objects and more like a set of arrangements. This does not drain wonder away. It deepens it. Knowing that a window's clarity, a gemstone sparkle, or a leaf screen comes from atomic patterns makes the everyday feel newly intricate. Atoms are not something you need to see to appreciate. They are something you can understand, and that understanding changes how you look at everything else. Reality gains a second layer, quietly present beneath the first. Everything you have ever touched is an expression of atomic behavior. Every surface you have felt, from warm fabric to cool stone, is your nervous system reading atomic interactions. Smoothness is tiny patterns in a material structure. Warmth is the transfer of vibrational energy. Stickiness is molecular attraction at close range. Hardness is resistance to rearrangement. Even the simple act of gripping a cup involves countless microscopic forces balancing at once. Touch feels immediate and personal, but it is also universal. The same atomic rules that shape a seashell shape your keyboard and your skin. This is why the material world is so consistent. Wood behaves like wood everywhere because its atomic and molecular structure repeats its patterns reliably. When you learn this, touch becomes more interesting, not less. You are not merely contacting objects. You are interacting with organized matter, built from the same atoms found across the universe, expressing themselves through structure, bonding, and force. Your hands are, in a sense, reading physics. To understand atoms is to glimpse the deep order of the universe. Atoms show that the universe is not a chaotic pile of stuff. It is an ordered system with rules that can be learned, tested, and trusted. Those rules are strange in places, especially in the quantum realm, but they are consistent. From that consistency, patterns emerge. Elements repeat their behaviors. Bonds form and break in predictable ways. Light carries signatures that can be decoded across space. With enough patience, you can look at matter and begin to anticipate how it will act. That is what science offers at its best, not just information, but a sense of structure beneath experience. Understanding atoms also brings humility. The same rules that shape your body shape distant nebulae. You are not outside the system. You are a part of it. And there is something deeply calming about that. Beneath the variety of the world lies a quiet order, and atoms are one of the clearest doors into seeing it. As we come to the end of our journey tonight, you might notice how the world feels a little quieter, and perhaps a little deeper. We began with atoms as simple ideas, tiny building blocks hidden beneath everything familiar. And slowly, they grew into something vast. We followed them from the hearts of ancient stars to the air around you now. From glowing auroras and distant galaxies, down into bones, breath, light, and memory. It's comforting to realize that everything solid and steady in your life is made from patterns that repeat, patiently and reliably. Atoms moving, bonding, releasing light, carrying energy, telling time, and cycling endlessly through worlds and living things. Nothing hurried, nothing wasted, just quiet order beneath the surface. And now, there's nothing more you need to think about. You don't need to hold on to details or ideas. Let them drift the way atoms drift through space, settling where they need to be. Allow your shoulders to soften. Let your breathing slow. Feel the support beneath you, steady and dependable, built from the same calm rules we've explored together. If you're still awake and feeling curious, there will be another gentle journey waiting for you on the screen. And if these moments of calm science have brought you comfort, you're always welcome to like, subscribe, or leave a quiet thought below, helping other sleepy minds find their way here too. But for now, simply rest. Let your thoughts loosen their grip and allow the night to carry you gently onward. Sleep well and good night.